Assalamu alaikum, sir. Welcome to our presentation. Today our presentation topic name is NFA to DFA Conversation, submitted to MD Monarul Islam, sir, lecturer, Department of CSC. I'm Hasibur Rahman Shifat. My ID is 241159959. Here is our teammate, MD Mahfuzur Rahman Firoz, MD Robiul Islam, MST Tania Akhtar, MST Parma Akhtar, and K Akhtar. So NFA to DFA conversation is a process of transforming a non-deterministic finite automation NFA into an equivalent deterministic finite automation DFA using the substate construction algorithm, where each DFA state represents a set of NFA state, ensuring a single clear translation for every input, making it easier to implement and understand. This conversation achieves determinism, allowing for one definite next state, and is crucial because while every NFA can become a DFA might need significantly more state up to 2 to the power n. Deterministic finite automation DFA is a mathematical model in computer science, a type of finite state machine that accepts or rejects string of symbols by processing them one character at a time, moving deterministically uniquely through a finite state of states to find a pattern or validate input. Crucial in complex text processing and pattern matching. Characteristic determinism. In a DFA, for each state and every input symbol, there is precisely one translation. Epsilon. Epsilon translation are strictly disallowed, ensure ambiguous and predictable behavior. Formal definition. A five-tuple, a DFA is formally defined as a five-tuple: Q, sigma, delta, Q naught, and F. Q, a finite set of states; sigma, a finite input alphabet; delta, Q into sigma Q, the translation of function; Q naught, element of Q, the initial state; F, element Q, the set of final states. Thank you, sir. Now I invite to continue this presentation MD Mahfuzur Rahman.
Assalamu alaikum everyone. Myself Mahfuzur Rahman Firoz and my ID 2411578. Today I will briefly explain two important concepts from theory of computing: deterministic finite automata DFA and non-deterministic finite automata NFA. First of all, we explain DFA. Here we see an example. First, look at this DFA example. This DFA is designed to accept all binary strings that end with 0, where the alphabet is 0, 1. It has two states: Q0, the start state, and Q1, the accepting state. From Q0, input 1 keeps the DFA in Q0. Input 0 moves it to Q1. From Q1, input 0 keeps it in Q1. Input 1 moves it back to Q0. So, if the last input symbol is 0, the DFA ends in Q1, which means the string is accepted. The transition table below shows the same behavior in the tabular form. Now our second slide, NFA. NFA full form is non-deterministic finite automata. Now let's talk about NFA. An NFA has the same basic structure as a DFA. Here with the 5 part: Q, summation, delta, Q naught, and phi F. But the main difference is, for the same state and input, an NFA can move to multiple states. It can also have epsilon transition, which do not consume any input. Because of this flexibility, NFAs are often easier to design, but internally they can do converted into an equivalent DFA. So, in summer, we say DFA has exactly one path for each input. NFA can have multiple paths and epsilon transitions. Both recognize the same class of languages. Thank you, everyone.
Assalamu alaikum. My name is Muhammad Robir Islam and my ID is 241159494. In this slide, I am explaining an example of a non-deterministic finite automaton, also called an NFA. This NFA uses the alphabet A and B and it accepts all strings that start with B, A, B. There are four states in this automata: Q0, Q1, Q2 and Q3. The automata starts at Q0. When it reads B, it moves on Q1, and then on reading A, it moves to Q2. After that, on reading B, it reaches Q3, and the Q3 is the final state. From this state, the automata can read A or B and stay in the same state. This means that once the string B begin with BAB, it will be accepted. Next slide, we move from an NFA to DFA. NFA are easy to design, but they are difficult to implement because they can have more than one transition for the same input. DFAs are easier to implement because they have only one transition for each input symbol. To convert an NFA into a DFA, we use the subject construction algorithm. This algorithm helps us to create a DFA that accepts the same language as the NFA. Next slide, I am explaining the subset construction algorithm. In this method, each DFA state represents a set of NFA states. The start state of the DFA is found by taking the epsilon closure of the NFA start state. This means all states that can be reached without reading any input. A DFA state is a final state if it contains at least one final state of the NFA. Transitions are created by checking where all NFA state in the set moves for each and each input symbol. By repeating this process, we get a complete DFA that behaves the same as the original NFA. Thank you.
Assalamu alaikum sir. My name is Tania. My ID is 24115 Today I will explain how to convert an NFA into a DFA using the subset construction method. NFA means non-deterministic finite automation and DFA means deterministic finite automation. In DFA, for each input symbol, there must be exactly one transition from every state. Now the problem statement the problem is we need to draw an NFA that accepts all strings ending with 1 over the alphabet 01 and then convert that NFA into its corresponding DFA. Draw NFA graph. First, we draw the NFA graph. Here, Q0 is the start state and Q1 is the final state. From Q0 on input 0, the machine stays in Q0. On input 1, it can stay in Q0 or move to Q1. State Q1 represents that the string ends with 1, so Q1 is the accepting state. Draw NFA transition table. Next, we write the NFA transition table from state Q0. On input 0, the transition is to Q0. On input 1, the transition is to Q0 and Q1. From state Q1, there are no outgoing transitions. This table helps us during the conversion to DFA. Conversion to NFA to DFA. Now we convert the NFA into DFA using the subset construction method. Each DFA state represents a set of NFA states. The DFA state is Q0 from Q0. On input 0 it goes to Q0, on input 1 it goes to Q0 Q1. Since Q0 Q1 contains the NFA final state Q1, this DFA state becomes a final state. After completing the transition table, we get the final DFA. This DFA accepts all strings that end with 1. The DFA is deterministic because each state has exactly one transition for each input symbol. Now conclusion. In conclusion, we successfully converted an NFA into a DFA using subset construction. This method ensures that the language accepted by the NFA is also accepted by the equivalent DFA. Thank you, sir. Assalamu alaikum.
Assalamu alaikum. I'm Parma, ID 2411568 Now I will talk about NFA to DFA conversion and also explain power equivalence and state complexity. In the above DFA table, in this slide we see the DFA transition table. At first the state column has only Q0, but the input column we get a new state called Q0 Q1. In DFA, every state that appears in the input column must be added to the state column. So Q0 Q1 is added as a new DFA state. Finding transition for Q0 Q1. Now we find transitions for new state Q0 Q1. For input 0, Q0 goes to Q0 and Q1 goes to nothing. So the result is Q0. For input 1, Q0 goes to Q0 Q1 and Q1 goes to nothing. So the result is Q0 Q1. In this way, all transitions are calculated. Completed DFA transition table. This slide shows the complete DFA transition table. There are two states Q0, Q0, Q1 and two input symbols 0 and 1. Each state has exactly one transition for each input, so the table follows all DFA rules. Final state identification. Now we find the final state of the DFA. If a DFA state contains a final state of the NFA, then it is also a final state. Here Q0 Q1 contains Q1, which is a final state in the NFA. So Q0 Q1 is the final state of the DFA. DFA diagram. In this slide, we draw the DFA diagram. Q0 is the start state, Q0 Q1 is the final state. All transitions are drawn from the transition table. Now the NFA to DFA conversion is complete. Power equivalence and state complexity. Now I will explain power equivalence and state complexity. Theoretically, NFA and DFA are equally powerful. Both can recognize the same type of language called regular language. But in practical implementation, DFA is easier to use and implement. However, when we convert an NFA to a DFA, the number of states may increases. This increases is called state complexity.
Assalamu alaikum. I am Noshin Samia Kea. My ID 2411558. Now I am going to talk about DFA, NFA and conversion. In a DFA, for every input symbol, there is only one possible transition. Because of this single fixed path, DFA is very predictable, efficient and practical. It is widely used in real-life applications such as compiler, lexical analyzer and pattern matching, where reliability and speed are important. Let DFA and NFA. NFA non-deterministic finite automata. In a NFA, for the same input symbol, there can be multiple possible transition and it also allow epsilon transition. Due to this, NFA is more flexible and easier to design, especially when describing or constructing a language. Although DFA and NFA are different in structure and execution, they are equally powerful. Both of them can recognize the same set of regular languages. An important point is that any NFA can always be converted into an equivalent DFA. This conversion helps in implementing theoretical design in practical system. Conclusion: NFA is flexible, DFA is practical, and conversion between them is always possible. Thank you, sir.